All right, kiddos, let's talk a little bit about what happens when we add something else to our aromatic compound. So we talked about electrophilic aromatic substitutions over the past couple of videos. And so what we're going to talk about in this video is what happens if you try to add something and you already have something there. So like, let's say that we've got a toluene molecule and we want to add a nitro to it. So what occurs then? So basically the substituents, okay, that's what we call something that's attached to the ring. The substituents that are already there, they have two main effects. The first effect is that they affect the rate of reaction, okay, how quickly it happens. We'll talk a little bit about this at the beginning and a little bit at the end of the video. And then the main thing we're going to concentrate on the video is they also are going to affect where the additions occur. So this toluene is going to affect whether we add this nitro group here, here, or here. So whether we add it ortho, meta, or para gets affected by the type of group that's up top here. So let's real briefly talk about the rate of reaction. So in the middle here we have a typical benzene, right? It doesn't look like it because there's an H there, but remember there's an H at each corner. So we're going to take that as reaction rate 1. And so what we're showing here is that if I'm trying to add a nitro group, an NO2 group, that having these groups on there affects that in certain ways. So you can see right away that having another nitro group already there really slows down the rate of adding more nitro groups, okay, immensely so, compared to adding it to just a benzene. And then we look over here and we see that, well, if I had a phenyl group on there, a hydroxyl group attached to it, if I had phenol, sorry, if I had phenol, or if I had a hydroxyl group added on there, that would actually speed it up a lot. That reaction would actually happen more quickly to add the NO2 on there. Okay, so that's part of the rate of reaction stuff. We're going to come back to that and talk a little bit more about the why of that towards the end of the video. So let's jump right in here and sort of talk about us adding something on and how that determines what the position is going to be. So if we have a toluene molecule and we're trying to nitrate it, okay, in other words, we're adding nitric acid to it, here's what we get for our products. So we get about 59% of the products will be the nitrate, the NO2, added at the ortho position. Okay, in other words, next to the substituent that was already there. About 37% of it gets added para, in other words, exactly opposite of it. And only 4% gets added at the meta position. Okay, so most of it, excuse me, most of it gets added ortho and para, and very little of it gets added meta. Whoops, didn't mean to move that around. Okay, so obviously we can see that the predisposition here is that if I've got this particular group, a methyl group, okay, what makes it toluene, that I'm probably going to send things to the ortho and para position. There are other groups that if we add them on are going to send things to the meta position. So like if there was already a nitro group on there, and I went to add another one, that second one would get added in the meta direction, about 93% of it. Now, you can see that that's not 100%, but I mean, in chemical production terms, that's a pretty high percentage, and so that's really indicative of how the reaction is going to go. So, we're going to call our groups then ortho-para directing or meta directing, okay? Ortho and para always go together, okay? Things get directed to one of those two locations. And then meta things go together, that the additional substituents get directed to the meta position. Okay, so we're going to talk for the rest of the video, most of the rest of the video, about how this happens or why this occurs in this way. So what things are ortho and para directing? Well, there are two types of things that are ortho and para directing. And again, you've got a sheet that you should have of stuff that you need to memorize or sort of commit to memory about ortho-para and meta-directing, which groups are what. Essentially, though, it breaks down like this. Alkyl groups, like that CH3 that we saw in the toluene, and then groups that have an unshared electron pair on the atom that is directly attached. Okay? So if I add a hydroxyl group, okay, as we saw there in the rate thing, there's an unshared electron pair on this oxygen here. Okay? If we add another oxygen, if we add some of these other groups here, we add an amino group, all of these things, what they all have in common is that they all have unshared electron pairs, and that's what's going to essentially direct things to the ortho and para position, and we'll talk about why that is. So, a lot of information on this slide. Don't freak out. Do your normal screenshot or pause it, take a second, copy it all down, and then let's talk about what's going on here. So this is the reaction that we started with. Toluene, I'm adding nitric acid. I'm trying to nitrate it, and this would be true essentially for any alkyl group. Okay. So what's going to happen is what we're looking here that really makes the biggest difference here. So what we're looking at here that really matters, what's really going to direct things in the case of alkyl groups to ortho and para is that, remember we've got resonance structures, right? So if we're trying to add stuff on, we're going to get a carbocation formed. It's going to be a resonant carbocation because the double bonds are going to be able to, remember they're not really shifting around, but essentially there's some position intermediate to each of these three positions. But here's what makes ortho and para favored for this particular reaction here, is that I'm going to circle this one real quick, okay, on the ortho. And then if I come down here and I circle this one for the meta, or I'm sorry, the para, meta, para, I'll get this straight, okay? If I circle those two positions, take a second, look at those and see what's different about those compared to all the others. Now, if what you guessed was that the that the carbocation formed where the substituent already was, then you were correct. These are more stable because we get a tertiary carbocation that is at least possible with an ortho and para substituent added. Because as we are showing here that we could shift around the double bonds, and again remember that we're not actually shifting around the double bonds in the charge, but as that is a possibility, this one position here for each the ortho and the para gives us a tertiary carbocation that is going to be a lot more stable than any secondary carbocation, and so therefore that is going to be the favored position. Now, again, doesn't mean it's always going to happen, which is why we get a small percentage that it doesn't work out for. But in general, that additional stability is going to mean that that's going to form a little bit more. So how does that compare if we tried to do the same thing meta? Well, if you look at each of the meta formations here, the carbocation that forms in each case is a secondary carbocation, okay? For meta, there is no possibility of a tertiary carbocation, and so that's going to make ortho and para form way more than the meta position does when we have an alkyl group, okay? So that makes pretty good sense. That sort of explains why alkyl groups are ortho and para directed, okay? So why would it be favorable to have ortho and para directing if it was an unshared pair on the initial group? So we're going to look at our phenol here, at our group that has a hydroxyl, an OH substituent. We're going to try to brominate that. We're going to try to add a halogen into that. So what happens there? Well, what's going to work out in that case is that instead of a more stable carbocation, because again there's not a carbon here because now it's an oxygen, what is actually going to happen in this case, you see, is that we get a whole 4 resonance structures, because what happens is that this oxygen or the nitrogen or whatever group up here has this additional electron pair possible is going to allow another position to form. And the position that you want to see that's forming here is this one right here. And this is not going to be, again, not going to be possible in the meta. Sorry for the drawing here. Remember, I'm drawing and not looking where I'm drawing here, so that makes it a little difficult. Actually, I'm looking at the drawing. I'm not looking at my pen. So these two positions here, what you should notice here is that what's actually happened is that the positive charge has been able to shift up, okay, to the oxygen itself. In other words, it's delocalized completely off of the ring altogether. And what that's going to do is it allows some additional stability for where we're adding in our second substituent. Now, what we'll see here is that that is not possible on our meta, right? Because there's no position here where the positive charge, where the double bond, could actually shift up here to the OH group like it can in the ortho and the para. And so that essentially is going to be our rationale behind anytime I've got that electron pair that's free there, that I can shift the double bond up there. I can therefore shift the positive charge up to that group, whether it's an oxygen or whether it's a nitrogen or whatever is up there that has the unshared pair. That extra shifting is then going to make it more favorable for us to form our second substituents at our ortho and at our para position, and less likely to form them at the meta. And again, it is possible for them to form at the meta. There's a small percent that forms there, but it is a small percent. Okay, so let's go on and talk a little bit about the meta-directing groups. So first off, what sort of groups are meta-directing? And I actually gave you a few examples here. These are not all of them. And again, you've got a list that has them on there. But essentially the way it works is that if the atom that is attached to the aromatic ring is positively charged to begin with, or is part of a multiple bond, so a double bond or a triple bond, with a more electronegative element, what that does is that it essentially pulls electrons away. Okay, and we're going to see what this does in the mechanism here in a second. But essentially, that double bond there, that electronegativity of the initial substituent is going to start to pull things away. So you see some of the examples here. Obviously, the nitro group that we just worked out for all of those that said that they were meta-directing, that's a big one. Our carboxyl groups that we're going to see all the time, the sulfonic acids that we get from sulfonation, our acyl groups from our Friedel-Crafts reactions, all of those things are going to be meta-directing groups. So how does that work? I mean, what's going on there to cause that to happen? Well, again, you've got a partial positive charge here, and this is, you're looking at this going, I don't remember there being a positive and a negative here. Remember that if we calculated the formal charge here of these things, that this nitrogen in the nitro group is going to have a positive, it's going to give its oxygen a negative. Of course, remember that's sort of a resonance structure. We could, the double bond could be here and the negative could be over there, but don't sweat all that. So what happens is that if I try to nitrate that again, that we want to shift things around in the resonance. So when I'm adding things on, remember you're always forming a carbocation. And what we don't want to form here is a carbocation where the plus is near the plus that's already on the nitrogen. And if we look real quickly at our ortho and our para positions, one of the resonance structures, and I did not draw them all because I was trying not to clutter up the slide as much as I did in those previous slides, but one of the possible resonance structures, whereas in our ortho and para directing groups it was great to have the positive charge here, particularly if you had a methyl group or an alkyl group up here, because that was a tertiary carbocation. It's actually still the same carbocation here, but what happens is I've got a positive charge here and a positive charge here in both cases. And we don't want to get positive charges near each other, right? They repel each other, and so that's not going to be very favorable. So what that means is that we want the positive charge to be somewhere else on the ring. And so meta, adding things on meta, allows us to shift that positive charge in all of the resonance structures away from the one that's near the substituent group, whereas ortho and para have at least one resonance structure where the positive charge is near the other positive charge. And we don't want that. That's actually going to be unfavorable, so it's going to shift it away, and it's going to cause those things to shift down to the meta position to avoid that. Okay? So there are a couple of things here. Oh, sorry, I didn't mean to jump over there. So there are a couple of things that you want to know here as we're thinking about these ortho-para and these meta-directing groups is, first off, what are the groups? Okay, so knowing those. So alkyl groups, things with unshared electron pairs, those are ortho-para. Meta groups are things that have a double bond attached to something highly electronegative. That's one part of it. And then the other part of it is to be able to explain why, what's going on, to be able to draw these resonance structures and say, hey, I know that the reason that I'm adding this on here has something to do with this positive charge, and I don't want a positive near another positive, so that's what's going to make it be meta. And if we jump back to our ortho-para, remember that it's going to have something to do with, is the carbocation more stable in the case of alkyl groups, okay, tertiary carbocation, or is it that I can actually further delocalize the electrons in the charge by shifting them actually off of the ring altogether onto something that has an unshared electron pair. Okay, so let's talk real briefly here at the end about how does this actually affect our rates of reaction. So we have two types of substituents here that we say, aside from ortho-para and meta, we can call them activating substituents, and activating just means it's going to speed it up. It's going to cause that reaction to happen more quickly, and deactivating that's going to cause it to slow down. Now here's the good news. For the most part, they fall into their ortho-para and meta categories. So generally speaking, ortho-para substituents are almost always activating. Now there is an exception here. The exception are the halogens, and that's because they're electronegative just like our meta-directing groups are. Okay, so halogens are really electronegative, and so they're going to tend to pull the electron cloud off. Okay, deactivating substituents, all of our meta ones plus our halogens are going to be deactivating, meaning that they're going to slow down the rate of the reaction compared to adding that substituent onto a simple benzene ring. Okay, now why does that happen? I'm not going to go too deep into this, but essentially what happens here is that it has to do with what does that initial substituent do to the electrons that are already in the ring. So basically, I'm going to consider yellow here an area of high electron density. And so when I add a methyl group on here, make a toluene, the electron density is still all in the ring. I still have all of those delocalized pi bonds going all around that ring. Okay? And so in an ortho and para group, a traditional one, a non-halogen one, all of the electron density essentially stays in the ring. Okay? And so that means that I can still get the reaction to happen more quickly because it's still a very electron dense, and so electrophiles are going to want to attack it more. In the case of our meta-directing, or something like our nitro group here, I've essentially pulled a lot of the electron density off, and a lot of the electron density has started to shift a little bit out to the substituent. There's still an electron dense region here, but it's not as much. There's a lot more of it sort of shifted back here. And so what that does is, now that the ring itself is not quite as electron rich, electrophiles are going to be somewhat less likely to attack it, and so therefore that's going to slow down the rate of reaction. Okay, a lot of stuff there, guys. Definitely a massive amount of drawings and stuff. So hopefully that helps you out. Hopefully the fact that we have a video, and of course we'll talk about this in class, will help you out as well. Thanks a lot, guys.